So to start with, we're dealing, as Philip said, both climate and the COVID-19 pandemic are two global interconnected crises. They're vitally dependent on evolving science. The speed of them is very different, of course. But over the last couple months, we've sort of asked, and I and others have asked the questions, of what does a cloud and climate physicist know about pandemics? Well, there's a couple of intersections that have actually arisen. There's some intersections on the physics of clouds, pollution, and there's some impacts on pandemics. As I'll demonstrate, when drops come out of your mouth, they're basically drops of salt water and organics. They behave somewhat like air and clouds does. And the environment and pollution is an intersection because it affects airborne drops. It also affects our lungs. Air pollution and emissions changes are occurring during these lockdowns, during periods of very different economic activity. This is a little picture showing a difference. It's an anomaly, so it's 2020 minus last year, but the blue shows a significant reduction in air pollution over most of the Indian subcontinent over the month of March or April, when most of India was locked down. There are impacts on air pollution. There's also some interesting impacts. You can ask the question, what does this mean for climate change? And there's some very interesting policy lessons that I think we can draw from this, and some insights, I would say. And finally, there are very large uncertainties in modeling pandemics, and that's vital. So here's a plot from a Columbia University model of the pandemic showing, this was published in March, showing estimated number of cases with no control measures over time, and then putting in control measures of different magnitudes and showing the number of cases. Well, there's a lot of uncertainty there. And this is a plot of the global average mean temperature predicted by climate models from 1950 to present and on into the future. Weather and climate scientists know quite a bit about prediction. And I think how we frame that can help us understand the epidemiological modeling and also vice versa. So I can actually I'll present some of these epidemiological models and the concepts in the context of climate models. So let's talk about the physics of clouds, pollution, and viruses in air. Basically, what comes out of your mouth, phlegm or sputum, depending on what you want to call it, is nothing but salt water and organic molecules. It's not that different than sea spray, although the size distributions are a little different. And the dynamics work like small cloud drops and aerosols, and how they interact with the air, how they interact with water in the air, and how they actually move around. So there is something we can say about this and things that we've learned from studying clouds and studying air pollution. So first of all, the thing to realize is that viruses are tiny. We speak in micrometers, so a micrometer is a millionth of a meter, it's a thousandth of a millimeter, or the best way to think about it is a human hair is about 40 to 150 micrometers. So one of these coronaviruses is 1/400th the width of a human hair, but that's not the size that matters that we're worried about. It's the size of the drops that matter. It's not the size of the virus, because the virus comes out of the body in drops, in liquid. There's two groups of these drops that people seem to exhale. Either aerosols, a small population, which are 1/20th the width of a hair, and there are lots of them, and then large spray particles. There are not that many of them, but they're big. So these are 1 to 2 times the width of a human hair. And these drops occur with breathing, talking, and coughing. So you don't have to talk or sneeze, I should have added that, to actually have drops come out of your mouth. And those drops can contain the virus. The large ones, these large spray, are going to hit the ground pretty quickly, on the order of something like a minute or two. They also will go about 2 to 6 meters, as this demonstrates here. The small drops, there's a much larger population of small drops, but it's hard to get these to go beyond 2 meters quickly. So this is because the drops are very small, they don't have a lot of mass, and they have a lot of surface area relative to their mass. It's like trying to throw a feather. You can throw a ball, even though it's bigger, a lot farther than you can throw a feather, and that's because of the ratio of the mass to the air resistance. So these do stay in the air for a long time, but they don't initially go very far. And you can see that 2 meters. We may have heard some things about 2 meters and social distancing. This is sort of where that comes from. And then dispersion is very rapid in the open air. So you have concentrations of these things that fall off quite fast. So does the virus actually survive in the air? And the answer is it appears to. The aerosols can persist outside of the body for some time. Viruses seem to survive in those aerosols as long as they're liquid or even beyond that. This study looked at aerosols over time. It looked earlier at SARS, so that was the sort of first coronavirus in 2003, and viruses in this most recent epidemic with controlled studies. And what they did is they sampled aerosols in the air after release at these time periods, and then they actually cultured them to see if they were actually viable, which is important. And it did. These were the fractions of them that were viable, so there is viability. Note that this is a log scale, so this is falling off quite rapidly. The half-life, the time at which half of them were still viable, was something like an hour. So after 2 to 3 hours, there's not many that are still viable. And they didn't test temperature or humidity. And note that the severity of illness may depend on the contact extent. So you're unlikely to get a severe case, it looks like, from just one virus particle. You need to be exposed to a lot of them. And that's actually why healthcare workers are at high risk, is because they're exposed to a lot of these virus particles. Let me see if I can get this to work. This is a YouTube video. It's from, whoops, I can just hit it. It's from Aalto University in Finland. Whoops. Maybe it'll play, maybe it won't. There we go. And what this shows is a model of a person coughing in a corridor, which is not dissimilar from a store, like shelves. And you see this aerosol cloud in the corridor, and it takes several minutes for the clouds to spread and disperse. And it's minutes. And you can also see the color indicates the height. And what's interesting is some of it gets lofted, and some of it is basically flowing with the ventilation system. And some of it is falling down to the floor. Those are the larger modes. And you can see that on the order of, there's an initial burst away that then gets taken up by the ventilation system. And after 5 or 6 minutes, most of it has hit the floor, but there still is a cloud of particles sort of sitting there in front of a person. So this is just something to think about that demonstrates this physics, basically. Whoops. And this is sort of where social distancing, as I said, comes from. So the 2 meters comes from scientific studies, both of the physics of particle spread and empirical studies of infection in high-risk environments. And the estimates are, this is from a recent meta-analysis, so looking at 172 studies, most of them in healthcare settings with coronaviruses, so either SARS, MERS, or the current coronavirus. And this is in healthcare settings, and this is outside of healthcare settings. Shows the risk reduction here of wearing a mask, and this shows the overall risk of infection falling. This is without masks, but just with distance. And you can see that if the absolute risk is on the order of 7%, that can pretty much get cut by a factor of 2 or 3 by just staying 2 meters away from somebody. So this is where we get the social distancing. It actually arises out of some of the basic physics of how air moves around and how these drops work. So now the question is, does temperature and humidity affect virus spread? And this is sort of the related question of why does flu peak in winter? There are many things that affect flu transmission and susceptibility of humans to flu. So one is temperature and humidity. And this is an experiment that was performed, a guinea pig experiment, where you take an infected guinea pig, you flow air at a given temperature and humidity, and you expose another guinea pig and see which guinea pigs get sick. And what they found was that at lower humidities and lower temperatures, you get more flu transmission. Well, this is the humidity in relative or absolute terms outside and inside. And so if you look at outside, the vapor pressure is the absolute humidity, and the indoor humidity, in the winter, it's much lower. So you do see lower humidity and obviously lower temperatures. But we do still see infections in warm climates, so this is not the answer entirely. You also note that susceptibility is different than winter. That means people get affected differently. With the same transmission, you can get different outcomes. Lungs are more prone to infection when they're dry, when the air is drier, and people's weakened immune systems can also be weaker in the winter because they're spending more energy to keep warm. There's less vitamin D from sunlight, things like that. So what has a cloud scientist like me learned? Well, drops remain in enclosed spaces for some time. I think we'd really like to know, and I don't know yet, whether the infection happens more in big or small drops. This matters quite a bit because the virus can last an hour more in enclosed spaces, particularly with small drops. There's too much dispersion outside to matter, which is why you hear about opening outdoor spaces long before indoor spaces. Social distancing is based on physics. You can't push small drops rapidly more than a meter or 2. And also the population of large drops still does fall off fairly rapidly as well. So that does tend to reduce infection rates. Masks, which I haven't talked too much about, can reduce transmission. This is critical for high-risk environments, but even for low-risk indoor environments, simple masks, like a simple reusable cloth mask, will stop most big particles and many small ones. So I actually wear a mask now when I go indoors and I'm around other people, especially if there's opportunities where I can't social distance, such as in a store. I wear it actually to protect you from me, not to protect me. So if I cough or something, it'll capture almost all the large particles that are coming out of my mouth before they get into the air. So that's something else to think about. Let's talk a little about virus transmission and pollution. So there was a study in Italy at the height of the epidemic there about 2 months ago where they actually found pieces of virus codes, RNA, like DNA for a virus, attached to air pollution particles. Pollution is less dense than water, and it might allow for farther travel. So this is very speculative because it's not clear this RNA, which was on a dry air pollution particle, was actually a live virus that could infect somebody. But we do know that air pollution causes lung disease, and it causes chronic lung problems. And what people have looked at is that pollution actually increases these ACE receptors that are receptors for the corona crown protein has to adhere to infect somebody. And there is a theory that people with chronic lung problems caused by living in polluted regions are more susceptible to severe coronavirus infections. There is a statistical analysis that shows moderate impacts of this. If you looked at the United States, the counties with higher air pollution also have slightly higher severity rates of coronavirus infections. But there's a lot of cofactors in that analysis, so that's not entirely certain yet. There are also, of course, pandemic impacts on pollution. So pollution is associated with transport and industry. Transport for people has dropped very significantly during global lockdowns, and industry is halted during the height of lockdowns. So this is for March 2020 during a lockdown in India. And what it shows is high concentrations of aerosols. These are not coronavirus aerosols. These are just general pollution aerosols, sort of what we would call haze. And then this is the same map for the month of 2020. And you can see there are some very large anomalies, particularly in the region where a lot of people live in the Ganges River Valley, that there's a very significant, almost 50% reduction in the total measure of the particles in the atmosphere. So the air was much cleaner with fewer particles during this lockdown. The clearest signal in the air is actually in transport emissions. So this is gaseous nitrogen dioxide. These are satellite measurements that you can make in clear sky. These are emissions from internal combustion engines. It's essentially the side effect of burning fuel is you burn a little bit of air, and so the nitrogen and the oxygen from the air end up combining at high temperature. This is from cars, trucks, and ships. You'll notice here this track in the Mediterranean is actually from ships going through the Mediterranean and up into Northern Europe. So this is 2019, which is a very typical picture. You can pick out a lot of cities. It's remarkable. You can actually pick out the transport networks. You can see the motorways in France pretty clearly going through some areas where there's the main ports in the south of France. Almost everything comes up this way in trucks, and a lot of cars come up this way to get into the rest of France and all the way up into Northern Europe. And then this year, this is what the map looked like. So in major cities, there were on the order of 50% reductions in this measure of the column amount of air pollution. And you can see that these transport networks are almost invisible now. You can't really see that anymore because a lot of the transport has actually stopped. And but air pollution is complicated. So this is from a station in London, just down the road from Oxford, and it shows a whole year's worth of data, over a year's worth of data. So last April and May 2019 is here. Red is the nitrogen dioxide again, and blue is actually ozone concentrations. And what you can see is a couple of things actually happened. Here you can see the drop in nitrogen dioxide again. It's pretty substantial. It's again about 50%, similar to other cities in Europe. And you'll see a rise in ozone. But you'll notice also there was a little bit of a rise in ozone last year. And there's some anti-correlation here. So there actually are other things going on. So there's some complex aspects of other parts of the air pollution chemistry, these volatile organic compounds. And if you have a lot of volatile organic compounds, you can actually increase ozone if you reduce this nitrogen dioxide. So the air pollution chemistry is complicated. Ozone also increases with sunlight, and for those of you in the United Kingdom and Northern Europe, you'll know that April and this later period here during the lockdown was a really sunny period. It was a record period for sunshine for a spring in the United Kingdom. So the other thing is these reductions, particularly for short-lived air pollution, may be temporary. So this is a map, this is a data from China, and it's calibrated by the Lunar New Year, which varies by a couple weeks every year. But it's sort of the Lunar New Year, or the period after that for 2 weeks is sort of like the Christmas or Easter holidays when everything shuts down in China and everybody goes on vacation. So what happens is you see a drop in emissions toward the end of at the end of that, and then they pick back up again in the beginning part of the year. And they, with the sort of pre-Christmas season, Christmas season, and then preparing for the Lunar New Year, there's a big rise and then decrease in emissions every year in China. This year they were lower, and then they stayed dramatically lower, much lower than the previous 4-year range. And there was a rebound, and so now they're actually getting somewhat back to normal in China as the country has come back to mostly normal and their infection rates have dropped. So now let's talk a little bit about climate, what this means for climate and climate change. And when I do this for public audiences, I always like to put everybody on the same page to understand what climate is and the difference between climate and weather. And the best way to state it is that climate is what you get, what you expect. Weather is what you actually get. What that means is climate is the distribution of possible weather and its frequency or probability. Weather is the chaotic evolution of the atmosphere. Chaos theory was actually developed and codified by a meteorologist in the 1960s to explain why the weather is not predictable. So this example shows the minimum temperature for any time in January in Madison, Wisconsin, and it represents basically the latter half of the 20th century. And the coldest day ever in Madison, Wisconsin was January 30th, 1951. This is a continental high northern climate. It gets really cold. In the winter, it can be like Siberia. And this is you can see this, the temperature is something like -38 centigrade, which is almost the same in Fahrenheit. It's really cold. But normally it's not like that. Normally it's on the order of something like -10, -15 centigrade, which is 10 degrees Fahrenheit or so. So this is the overall climate, and it just so happens that one day you get an extreme weather event and it gets really cold. So what is climate change? Well, climate change is when this distribution shifts around on average. So if you take an existing climate, say we're looking at temperature again, and we have an average temperature here in the middle with a high probability of occurrence, low probability of either very warm or very cold. So our January 1951 day would be somewhere over here. And under climate change, that shifts. So the probability of getting that same cold temperature, you get less cold weather. It's almost zero. But the probability, which is the area under this, the amount of space under this curve, the probability of getting really warm temperatures and record warm temperatures goes up quite a bit under climate change. So what does, we're sort of experiencing this as a result of the rise of greenhouse gases now. What does all these changes to emissions, so I showed air pollution, but that also means that things like long-term greenhouse gases like carbon dioxide will change. So what happened to the fossil fuel use and energy use, for example? Well, this is a forecast from the International Energy Agency that was published last month based on the demand reductions due to coronavirus and averaging them out over what was going to happen for this year. And what you can see is that the estimate is there's a huge drop in coal use. It's less drop in natural gas and a huge drop in oil. The oil drop, of course, is associated with transport, mostly transport reductions and transport fuels. A small reduction in nuclear energy, but actually an increase in renewables. So renewables are essentially free once they're installed, so why not keep them moving? Coal is actually, it's difficult to stop and start if you don't know your demand, and it's bulky to transport. A lot of the cost is in transport. So if you don't know how much you're going to need, it's not a good fuel to have. It's easily an optional fuel. And of course, oil, if you don't need it, you don't need it because nobody's using it. Whereas these other sources are used for fixed energy, and fixed energy sources we still need to, well, power our webinars, for example. CO2 emissions are actually, as a result of these drops, are projected to fall 8% in 2020. During the lockdown, the global reductions during the height of the lockdown periods were something like on the order of 20%, 25%. And to put this in perspective, on an annual basis, that's going to be the largest annual change ever in total emissions. However, this is the overall level of emissions over time, starting in 1900. It just brings our emissions down to levels we haven't seen since 2010. So this is not going to do anything to stop climate change. It may delay it a little bit, and it may accelerate some changes in the energy markets. But, I mean, anything is good, right? But there's a few interesting lessons here, I think, when we think about climate and climate policy. So we've stopped 90% of air travel, almost all the commuting, and 75% or so of car use. We've had huge reductions in transport fuels. This results in about a 20% cut in fossil fuel use. There's still 80% of the 75 to 80% of the fossil fuel we're still using. We're doing that to keep our regular society moving, to move things around like food and provide energy to heat our houses and to power our devices. This doesn't solve climate change by bringing our economy to a halt. We need to evolve it, not stop it. So we're not talking to people that you have to go through another lockdown to stop climate change. That actually doesn't do it. And it also says that non-essential travel and aircraft really don't have a lot to do with climate change. There's these fixed power plant sources. This is a huge impact, and the embedded carbon emissions in our energy system and in our transport system are things that we need to start evolving away from. The good news is that renewables have held up. We've seen the largest reduction in dirty fuels. And the other good news is that fixed sources are easier to change over time, like our power systems. So for example, it means that we don't need everybody to have an electric car as long as our fixed sources of energy, and most of those are carbon neutral. So that's important also, that some of the hardest technologies to develop are not we can solve climate change or reduce it without actually resorting to everybody being forced to do that. And also to note that the fossil fuels, and especially coal, are becoming more expendable in our energy transition. Coal is the first fuel to go. It may continue to be the first fuel to go, and this pandemic may help exacerbate that transition. So that's a good thing. All right, so let's talk about, I'm going to finish up with talking about how we model weather and climate, and also then a segue to how we model viruses. So weather and climate models it's basically an accounting exercise constrained by physical laws. What we do is we take a grid of points on the planet and we make a giant spreadsheet, and we make a spreadsheet at every point. This one happens to be, if you can see closely, it's actually a spreadsheet in dollars of sales of some company. But if you think of these entries as being water, heat, wind, salt, carbon, all kinds of physical properties of the system, we account for those at each grid box. We have processes that change them from one to the other, like condense water in the air into a cloud, have it fall out as precipitation, have it hit the land surface, have it run off into the ocean. And we solve equations for these processes at every point. We then advance in time and space and move the air and the water around. And we repeat this a lot. And we repeat it at every point on the planet. So common problems are that many of these processes are hard to describe at the right scale. We have these imperfect representations. So if you have a cloud that looks like this, that's this huge population of drops, at the scale of a climate model, which is miles, maybe many miles, maybe 50, 60 miles, maybe if we're lucky with a weather model, still a couple of miles, we might get two numbers to describe all the gradations that you see in the structure in this cloud. And we often have to fit uncertain parameters in these transformations from data. Well, how do you model viruses? It's not entirely dissimilar. You have basic physics of transmission. We talked about clouds of viruses, 2-meter distancing. You can derive potential infection rates and susceptibility of people. You have different locations. We have cities. We have different units of society. And you have a transmission rate that depends on people's contact, people's motion between them, their personal hygiene, how close they are to each other. And you can build a model of these things. And one of the leading models is sort of based on the Columbia University model from Jeffrey Shaman's group. We've heard some talks by. So you have susceptible people and you have exposed people, and then they actually get infected, and then they can infect the susceptible people again. And you have this N, which is actually a transport term. So it's the number of people moving in or out of a region. So you start with no infections, and you start with everybody, lots of susceptible people. Nobody gets exposed until you bring in the infection from somewhere. And that gets brought in with a map of how people move around. This is a network of commuting in the eastern seaboard between city pairs developed in this model. And you can basically then predict, you can put all this together and try to use data, which is here shown with the latency period, the number of susceptible people, the reported infections, and the number of people commuting to actually try to fit all this. And this is done, this was developed actually for the seasonal flu. And then you can run different scenarios to adjust the parameters to optimize the fit to past data. So for example, this is a virus forecast. This is for Salt Lake City, and there was data that you fit the parameters to, and then you run it forward with perturbations to those parameters that give you a spread of outcomes. This is called an ensemble of forecasts. And then you get actually a cloud, and then you see the actual data, that it did okay, but it really didn't get the peak. And ILI means influenza-like illness. So it's just a scaled measure of influenza. And then you can do this for different locations. Salt Lake City is here. You can describe how things move around, and then you can get a rate and predict it over time in the United States. These are rates over time, different years for different states. This model has been repurposed for COVID. You take 375 cities in China. This was done in January right before the lockdown, just as everybody was traveling for the Spring Festival. And it was trained by looking at travel records from apps in China and trained with data assimilation of cases, locations, and times. And you can fit the number of undocumented infections in the model and actually fit this the estimated reproduction rate in the population. So they're very powerful tools that are being used. So now let's talk about uncertainty in these models. That's the last thing I wanted to cover. For climate, we're talking about how bad will climate change be? What's the global average surface temperature in 2050, for example? For weather, we're talking about what's the weather going to be tomorrow? Is it going to rain? What about next week? And for COVID-19, how many infections are we going to have in the UK in the next week? Or how many ventilators are you going to need in the next month? How many hospitalizations is going to result? Well, weather and climate scientists know something about predictions of uncertainty. Weather and climate prediction have different kinds of uncertainty, and this is useful understanding even for virus models. What we care about for weather prediction is a 1-week time horizon. The uncertainty tomorrow is very dependent on the weather today. So if we're at January 30th, 1951, it's really cold. Is it going to be really cold tomorrow? Well, it might be. It depends on what's happening what the weather today is upwind of us. Is there a storm coming? Is sunny weather coming? Is warm air coming? That's going to shift us around on this distribution from day to day. It doesn't change the climate, though. For climate prediction, we worry about decades to centuries, and the uncertainty in 50 years is different. It doesn't matter what the weather is today for the climate in 50 years at all. And that's a very different way to characterize uncertainty. The weather uncertainty is what we call initial condition uncertainty. That dominates. This shows the total amount of uncertainty and the fraction of that uncertainty or the portion of that uncertainty from different sources. This is the weather uncertainty. It's the initial condition uncertainty. For climate, what actually matters in 50 years is how much CO2 is in the atmosphere. And that's the scenario. We don't actually predict the CO2 in most of our models. We specify the CO2. It comes from data for the past, and we predict it from estimates in the future from other models of energy use. And all throughout this, we have a constant, which is the model uncertainty. Initial condition uncertainty fades over time. That's not needing to know the weather today to get the climate in 50 years. And the scenario uncertainty is pretty much zero on the weather scale. We know how much CO2 is going to be in the atmosphere tomorrow. It's pretty much the same as it is today. And then there's this constant of model uncertainty, which actually in the mid-scale is the largest part of the uncertainty as both these things drop off. And for viruses, we're actually not that dissimilar in the way you can characterize the uncertainty. So what is the weather today, or how many people are infected, for example? For the model uncertainty, it's how to represent clouds or how to represent the virus transmission. And for the scenario uncertainty, what are the emissions of CO2, or what social distancing measures will be put in place? So getting data to constrain these things is critical. For weather climate, it's actually kind of interesting. We know the small scale, the physics of cloud drops, and we know the large scale, the global temperature, but we have a hard time describing an individual cloud, you know, at the scale of 500 yards or 500 meters. For viruses, we also know the small scale, the physics of drops, the biology of infections in bodies, some of the disease outcomes. We also know the large scale, the death rates, the hospitalization, the snapshots from virus testing, but that intermediate scale of person-to-person transmission is actually very difficult to model. So here's some examples of weather forecasting. Just quickly, this is initial condition uncertainty. If we talk about knowing the initial state and the evolution over time of a forecast ending up in some region of space, you can start from slightly different locations and you'll get a very different trajectory, even if they go through the same sort of initial point. So what we do is we do this. We run a spread of trajectories, usually varying the data that comes in, and you get a forecast in a range, either one forecast, but you also get a range of forecasts. And that's smaller than the total range of what the climate would tell you. Again, it's that one point and the regions around that one point on our plot of the temperature for January in Wisconsin. And what data goes into a model? Well, this is the initial conditions for weather model. This is from Tuesday. This is from ECMWF, which is the weather center down the road in Reading. And this is all the data that goes in. It's mostly over land, but it's something like 125,000 observations in 6 hours. More data gives you better forecasts. This is actually an ensemble flu forecast. This is similar to Salt Lake City, but it's showing a whole bunch of different ensemble members with different parameters that are trying to fit the data, and then they evolve over time. And this ensemble forecast actually does capture the entire range, the cloud of where the peak might actually occur. And it also, you can build a probability of these outcomes actually occurring in the model. The initial conditions for something like this, and I pulled these, this should be somewhat topical for people. This is from the Public Health England website on Tuesday, and this is from the Cabinet Office Briefing Room's presentation from the Department of Transport on Monday. It shows the transport use in the UK as it fell off after the pandemic, and its current slowly going up. You can see there's a weekend effect. That's these dips right here with the gray. And then this is the lab number of confirmed cases in England by specimen date. And again, there's a weekend effect. People don't get tested on the weekend as much. But you can put this into the model to then figure out how the virus is going to spread. So almost done. So again, the last thing is the scenario uncertainty. The future depends on human policies that are outside of our models. So we run ensembles of scenarios for viruses or climate models. So if you change the social distancing policies, you'll change the number of cases, you'll change the timing of the cases, you'll change the transmission rate. Likewise, if you change the amount of greenhouse gases in the atmosphere, so these are different measures of forcing the climate system, you get actually a different response in the global temperature. This plot also shows the model uncertainty. This spread is something like 30 or 35 different climate models for 2 different scenarios. What it actually means is by sometime around 2050, 2060, the model uncertainty you can see doesn't dominate. What really, the climate of the future is our choice. It's the scenario. It's sort of like saying the epidemic of the future next month is also our choice. It's what we as societies choose to do to actually control it. And what, if we come up with a vaccine, this changes. If you come up with better treatments, this also changes. So these are used to inform policy. So how much of each of these things should be allowed? How much social lubrication should actually be allowed? How much emissions of CO2 should be allowed for any desired outcome? Well, for COVID forecasts or for climate forecasts, these scenarios are critical. The biology is constant for epidemics, drops for viability, the comorbidities that cause some people to be more susceptible. But social distancing affects transmission, and that affects the reproductive number. That's the scenario uncertainty. So this is a real-time application of how uncertainty and policy decisions are used to interact. For example, do we open the pubs in the UK or not? So in summary, I think there's a number of different intersections and interactions between climate and COVID. They're sort of parallel global crises, but on very different timescales. And they interact through both the physics of cloud pollution and impacts for pandemics. Viruses spread by talking and breathing. Masks will likely help. Social distancing helps. Being outside helps. And lung damage from pollution may worsen the effects of the virus. So that may be one reason why we see some regions having more severe cases. And our world is now upside down and people have stopped moving. Our air is temporarily cleaner, but climate change will only be mildly affected by COVID. It tells us that stopping transport is not really the issue. Renewables are benefiting, and there are some lights in this about how we actually can move forward to restructure our economies and come out of this in a greener fashion that also helps us do something like about climate change. And finally, how do we predict the future? Where are the sources of uncertainty? If you think of them as initial condition model and scenario uncertainty, that helps you get policy guidance. So most of these models, particularly of academics, the more data you put into them, the better they are. So if you can test and trace cases, if you're capturing more of the reported and more infections, not letting infections go undetected, that gives you better policy guidance for things like social distancing. So ran over a few minutes, but those are the intersections I wanted to talk to you about today. So thank you very much for listening.
Fantastic. Thank you very much, Andrew, for a fascinating talk. I think the meetings work wonderfully online. The only thing, the applause never really is the same. So thank you for a fantastic talk. But I noticed quite a lot of activities in the question and answer, and I'll just pick some questions for now. We may not go through all. People still feel free to add questions as you like, because there's also opportunities after we're done to answer some of them in text and in person maybe. But let's start from the beginning. There's a question by Amoga, and the question is, can we expect any slowdown in the process of melting of polar ice caps due to the current situation?
I would say probably not. The polar ice caps are subject to extreme variability and on decadal timescales, and that's really a long-term thing. If we sustain a drop in carbon emissions that's substantial, or we start to turn things over, I think we may see some changes, but I don't think we'll be able to detect anything.
Great, thanks. There's actually two questions roughly about sources, about fixed sources. First one, an anonymous one. If fixed sources from power plants dominate the source term, would this not point to carbon capture of emissions to be a primary target for massive emission reduction?
I think carbon capture is an option if it works, but I think it hasn't been proven to work in a way that's economic. So I think I'm a big fan of letting economics decide what the most efficient way to actually reduce carbon emissions is. If it happens that capture is safe and it's efficient and it's cheap, then maybe that should be part of the mix.
Great. So there's a related question also about fixed sources from Mark Richardson. When highlighting only a 20% decreasing greenhouse gases and thus the dominance of fixed sources, I'm curious, how does agriculture stack up to the fixed sources?
Well, agriculture is part of in what I've shown, agriculture is part of the fixed sources because all that's continued. So agricultural emissions either associated with mechanized use of equipment or fertilizer, which is usually produced industrially, all that's continued. I don't have offhand the numbers of what that is, but that agriculture is part of the fixed source. So that actually is another target potentially for emissions reductions is in the agricultural sector.
Great. So I'm going a bit random through the questions here. So the question by Peter Reed. He asked, perhaps I missed something, but why does initial condition uncertainty decrease with increasing lead time? One normally expects this uncertainty to increase with lead time.
Initial condition uncertainty, no, it decreases with lead time. I don't know where.
Okay, might have been a misunderstanding.
Yeah, I apologize. No, it definitely, initial condition uncertainty, if I go back to the plot, it's definitely, this is it falling off with lead time. That's the lead time for the prediction. So it's making a prediction now for 50 years out.
Okay.
I think he's thinking in terms of some of the shorter term weather forecasts, which is different.
Great. There is a question by Annabelle Cook, who asks, is it possible that changes in emissions and resulting pollution will impact the development of the Southern Hemisphere ozone hole this autumn?
I would doubt it. I don't see a strong link, no. Even, I mean, the fires, the biggest perturbation of the Southern Hemisphere was actually the emissions from the Australian fires last fall, but they're pretty much out of the atmosphere by the time the ozone hole is setting itself up in a couple more months.
Okay, so there's quite a few questions about transport. So that was a one that people picked up. So Ray Piambert asked, how can you say stopping transport is not the issue when transport accounts for about a third of all emissions and is in fact responsible for most of the rise in US emissions? Agreed that it's transport emissions rather than transport itself that needs to stop.
Yes. So I don't think that's dissimilar of what I said. So if you roughly say that transport emissions, divide them into two, one is sort of cars and one is sort of trucks. If you cut out most of the cars, a lot of the truck traffic was still there. So that is transport emissions, but that's more of a fixed transport base. So even if you reduce carbon emissions by 30%, I still don't think we're quite there. It's that other 2/3 that we have to actually attack as well, or 70% that we still have to attack. So I don't agree. I agree with what Ray was asking. So
great. There's one from Gaurav Dubey. Do these good news about changes in use of energy and renewables hold in general across the globe, or are there geographical variations in there?
I do not know. I think you could go to the International Energy Agency website and you could download that publication, and there may be geographic there may be a geographic breakdown of those numbers that I showed. I only looked at the highlights of that report.
And there's a question by Andrea Bragas, who asks, is there anything equivalent to herd immunity in climate change managing? Which is actually an interesting question.
Ooh, that's an interesting one. Herd immunity. So herd immunity would be that you don't get as many infections because you're reducing the transmission. So I don't know what the equivalent would be. I mean, the equivalent of, there may be some equivalents. So for example, the equivalent for ozone destruction was that they developed different chemicals that actually broke up sooner, so they didn't actually destroy ozone. They disappeared in the atmosphere quicker. So if you had something like that, herd immunity might be if we had some saturation as we emitted more CO2, it did less, but we know from our physics there's really no saturation of CO2 at the levels that we're actually going to achieve. And so maybe the interesting message to that is, whereas herd immunity is an option for virus policy, herd immunity, in other words, not doing anything and just hoping it goes away, or hoping it saturates, or hoping all the ice caps melt and it stops warming, is not a good solution for climate change.
Great. So there was a more general question from Ari Luna. What are the solutions to tackle the two issues that you consider to have the most potential for the future? So that's a big question, obviously.
Ooh, well, I don't know that I want to get into policy guidance for viruses, especially because they might send me down to Westminster or something. But I would say for climate change, I think it's pretty clear that we just need to take the fossil, we have technologies to take the fossil fuels out of large parts of our energy sector. And we should start with the ones that are easy. You know, if you get rid of coal and start replacing it with renewables, you can make a huge difference. If you price things accordingly by their climate change impact, people will move in the direction of carbon neutral sources, and they'll do so in a very efficient way. So I think those technologies exist, and the pathway forward is pretty clear if we have the will to do so.
Great. There's actually one interesting question that I pick up, but we will answer them in the chat. That is Moyle Julian asked, any books or readings recommended for physics students interested in climate change? It's a fantastic question, but I think it will be best if we provide some in the chat window after we conclude. But I think it's a great question.
Oh, I can answer, well, although I will answer it online because I wrote a book on this, so I get to plug it. Demystifying Climate Models has a primer on climate change and a non-technical primer on climate models. It's there's no equations in the book, and there's a bunch of figures in it. So and it's also free. Demystifying climate modeling. You can search that on the web, and you should be able to find it. You can download the book for free from Springer.
And I should mention there's obviously plenty of good books out, and we can maybe provide a few more later on. So I think we should probably wrap up soon. Maybe just to read out a comment from Carsten Haustein, who says herd immunity in climate would be we all go extinct. Sad but true. That's an alternative answer to that, but it's at least one interpretation. I think many of the other questions are related to transport, and I think we probably don't want to go into all of these now because we addressed already some of them. There's a question, maybe one last question from anonymous attendee. When the lockdown is lifted, would the virus change its infection rate due to the back of pollution?
Right, so that's a question. It depends on whether the pollution is doing one of two things. The pollution could either be transmitting the virus more effectively, or the pollution could be making people's lungs worse. I don't know exactly how well people's lungs recover and how quickly from the loss of pollution, or the pollution going away, because it is sort of a chronic issue, but potentially that might matter. I'm not so sure I believe that pollution particles are going to be a big way to spread the virus. But just by what I know about the number of particles, the way people seem to get infected versus the number of pollution particles in the air, it's a lot lower, particularly because they're in the open air. So I think there may be issues with lungs that maybe, because I have heard anecdotal reports that asthma sufferers and other people are feeling better during the lockdowns in some places because of the reduction in pollution and particles.
Great. I think that's probably a good time to wrap up the questions that we take live. Andrew will hopefully stick around for a little bit and we can go through the open question. There's still 18 open questions in the question and answer, which is fantastic. So we'll take the rest of them offline. So thank you very much again, Andrew, for a fantastic lecture. Very interesting. Thanks for everyone, to everyone for attending. We had almost 300 people attending, which is fantastic. And I think it really shows that making lectures available online also in the future, even once we are able to go back, will be great for many people to attend. So thanks to everyone and also the other organizers, in particular Helen. And there will be another announcement for future public lectures soon. Thank you.